Oh, hello there. My name is Eddie Tuck, and I'm a member of the Hovercraft Project. I'm here to talk to you today about our experiences leading up to and comprising of Freshman Engineering Design Day. Members of the group include myself, Paul Burke, David Glenn, and Gabe Neuber. I hope you enjoy our presentation.
In order to do our Hovercraft project, we had to implement the engineering design cycle, which consists of 5 steps that repeat continuously until you're finished. The first is define your problem. Next, you need to search for solutions. And then you must narrow and select. Then you must build, and once you've built, test and check. And it continues until you've defined all of your problems and gotten them all out until your product works. For our Hovercraft project, we defined our problem as build a working hovercraft that we can steer through a carpeted 15-foot width multiple turn course using less than $40. And we did just that.
Step 2 of the engineering design cycle is search for solutions. First, we had to come up with a solution to our 2 problems, lift and propulsion. In the beginning, we decided that a hairdryer would be our best option for lift, but after careful consideration, we decided it was not going to work. Second, we went to the leaf blower, but with the model we chose, the leaf blower would be too heavy and it wasn't going to work. We then went to the computer fan. The computer fan worked for everything we needed it to, but we still weren't sure, so we kept it and went on to the next thing, the vacuum. The vacuum would have worked, but we couldn't find an appropriate vacuum that fit the size and the velocity that we needed, so that was crossed off, and we ended up going with the computer fan. Next, we had to deal with propulsion. First, we tried computer fans, but they did not have enough velocity to overcome the friction force and get the thing moving, so they were crossed off. Next, we tried to add cones to our fans to increase the pressure that they were putting out. The cones did increase the pressure, but it wasn't enough. We ended up going with our last effort, the RC car. It started on top and rolled off and dragged it like a trailer.
Step 3 in the engineering design cycle is narrow and select. Coming into this step, we had several options that we could have used for furthering our product and using for our final design. We decided to narrow it down between the 2 basic designs we had. One was plywood with a leaf blower engine, and then the second one was a piece of styrofoam with an electric motor that would provide the lift. We also had several options to use for skirts, and we decided to narrow it down to a trash bag skirt. We ended up deciding to go with the styrofoam model with computer fans because it was lighter weight, more accessible, and the total product cost would be cheaper.
Step 4 in the engineering design cycle is build. We started off with a sheet of styrofoam, which we then cut a hole the shape of our fan in the center of. We then proceeded to put our fan in the middle and hot glue it in. Then we took a piece of trash bag plastic and cut it out to the outside perimeter of our styrofoam plus 1 inch. This we're going to make into our skirt. We then took that same sheet of plastic and cut out the inside diameter minus 1 inch. We then folded it over and hot glued it to the outside edge of our styrofoam. Then we took 3 9-volt batteries and hot glued them to our project. We then wired the batteries in series, giving us 27 volts to power our fan.
Step 4 of the engineering design cycle is test and check. Now, the first thing we had to test was our propulsion system. Our initial idea was to have 2 fans right here, computer fans slightly smaller than this one, propelling it forward and turning it. But those weren't powerful enough, so we had to alter our idea. So we moved the computer fans back here, and we attached paper cones pointing downwards to increase the pressure. Those didn't work either, so we went to our backup idea, which was an RC car mounted on top, which would drive off and then tow the hovercraft behind it like a trailer. Once we decided our propulsion technique, we had to slightly alter our weight distribution here because it was moving towards this way. So we attached these 2 plastic baskets here and filled weights in each side to balance our weight.
This is our skirt. The white plastic you see around the outside of it. It's comprised of a trash bag, and its sole purpose is to contain the air pressure generated by our fan up here. Our fan is a PC computer fan that is designed to act as a large volume air mover, and instead we're using it as a compressor to create a light pressure underneath our hovercraft. The pressure held in by the skirt and the body of the hovercraft, generated by the fan, is what actually lifts the hovercraft. The total amount of force is the surface area under the body of the hovercraft multiplied by the pressure inside. The voltage for our fan comes from these three 9-volt batteries you see here. We're running 27 volts. Up here we have our power for motion. It's an RC truck that we purchased. The truck starts on top of the hovercraft. Then we plug the hovercraft in. If I can find out where our plug went. Oh. We plug it in. And it creates a pressure underneath causing lift. We then drive the truck off and we can tow it around.
Yes. Yeah.
Go, 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 go.
Come on. Go, baby.
Is it not going?
Here. I can't, can somebody steer or hold the antenna? Go with it, go with it, go with it.
Go, go, go.
Come on. Go with it, go back.
At Freshman Engineering Design Day, we didn't place, but we kind of attribute this to the fact that we bent the rules using an RC car to pull the hovercraft. It wasn't explicitly stated in the rules that we couldn't do that, but we feel that it negatively pushed the judges against us. So they actually told us over the intercom that they were going to make a new rule next year prohibiting students from using an RC car to pull their hovercraft.
One of the lessons we learned this year with our Hovercraft project was that just because something sounds good on paper doesn't mean it's actually going to work. Early on, we had a lot of ideas that we all agreed upon, but once we started testing them, they didn't work out quite so well. And this involved a lot of time, and by the end, we didn't have any designs that really worked that well. This led to our final model. Another thing we learned is judges really frown upon RC cars. One piece of advice we have for next year's freshmen is time management. When you schedule a meeting, get there on time, and while you're there, actually work on the project. It can be difficult to stay on task with 4 people who want to just hang out.